your information reminder. And then I will post the answer key for today's sometime this afternoon. And I'll also post 8, 9, so you can do that whenever you want. And then 5 and 6, I'll post it after we do it. Okay, so go ahead and take a shot at this, and then I'll remind you what it is. If you don't remember, this should take just like a minute. So categorize these as ionic or covalent. When we say molecular, we're implying covalent because compounds, ionic compounds, don't form molecules. Okay, so this is important because the naming is different for ionic and covalent. So you have to be able to identify which is which. So ionic is metal and nonmetal. Covalent is just nonmetals. The other thing to remember is in ionic, that nonmetal might be substituted with a polyatomic ion. But those are still nonmetals, so they're just a group of nonmetals. All right, so that means this guy is covalent, that's covalent, this is ionic because platinum is a metal, and that's covalent. So this would be the first step in how do I name these? Determine which it is, then you use the separate rules. Covalent is the one with prefixes. Ionic is where you just name one and name the other. And if it's transition metal, you got to use the Roman numerals. The key point about ionic is that they have a fixed ratio. So in ionic, you only would have calcium and chlorine in this ratio, 1 calcium to 2 chlorines. Whereas in covalent, you could have, like if we're doing, I don't know, oxygen and chlorine, you could have OCl or you could have OCl2. The ratios can be different between any two elements because you're not trying to balance charges. In ionics, you're trying to balance the charge. So you have to have 2 chlorines because they're -1 for every 1 calcium, which is +2. Okay? Okay, a little more concept-based now on this one. So take a minute and try to identify, there's none that are atomic elements. It separates these between covalent element versus covalent compound. So pay attention to that versus ionic compound. So label these as each. I'll give you a minute to do that. So initially people might be like, how do I tell if it's ionic or covalent if the elements aren't labeled, right? How do I know? Well, B and C, you can tell, are these individual units that are separated from each other, and same thing here. That is an indicator that it's a covalent molecule. Ionic compounds do not form these individual units. They form a cluster, however big the crystal of that thing is, of the different ions. So they're staggered, positive and negative, but there's no distinct amount of them. It's not like 1 and 1 or 100 and 100. It is a ratio that could be any amount as long as it's, in this case, 1-to-1 ratio. Okay, so this one is ionic. These two are covalent. Now, it does separate covalent compound. That would be this one because it's different elements, whereas this one would be a covalent element because it's just one type of element. Okay, so this would be something like Cl2. Remember the diatomics? There's 7 of those, H2 over here, and then starting at nitrogen and making like the shape of a 7. So N2, O2, F2, Cl2, Br2, and I2. So those are the ones that you're never going to see by themselves. Either they'll be in a compound like HBr, but you'll never see just Br by itself. It'll always come as Br2. So when it says like hydrogen gas reacts with such and such, it doesn't mean H, it means H2. Okay. All right. We're going to do 34 and 38 together. I want you guys to do these like do A and B for one and then A and B for the other. If you have time, sure, go ahead and do the other letters. But this is pretty typical of the back of the book problems, is it'll give you multiple parts that are practicing the same thing. So go ahead and do A and B if you have time, the others, and then we'll go over them. And if you don't have time to do the others, like I said, you can go look at the answer key for those. Okay, so A and B on both right now. Okay, so in 34, silver is a transition metal, but this is one you guys are supposed to have memorized that it's only +1. So the compound that it's going to form, I just realized we could have included the next one in it as well. Oh, well. The compound that it's going to form is going to depend on the charges of the two, so +1 and -1. So that compound is AgCl. Now, in the third question that I should have included with this, they give you the name and then expect the compound. Those are basically the same question, okay? So here it says silver chloride. In the, whatever number that is, 44, it would have just said silver, sorry, I just said chloride. Here it says silver and chlorine. In the name, it would have just said silver chloride. Okay, so they're not that different if you're given the two elements, versus if you're just given the name. In the following one, and maybe we'll just do those together for the example's sake. In the following one, these are transition metals primarily. And so, except for D and E. So they're giving you the Roman numerals to indicate the charge. Okay, so in D, it doesn't give you the charge, just like the ones in the previous question, whatever that number was, because you know them based on the location. So calcium's in the second column, so that's going to be a +2. Fluorine's in the 7th column, so that's going to be a -1. So when those form a compound, they're going to be CaF2. Again, ionic compounds are a set ratio. You don't get to have something that's a compound of CaF3. That doesn't exist, or Ca2F. There's only one correct ratio. If you have, like in A, if you have a transition metal, that's where they have to tell you the charge. So that's why it says copper 2. It's telling you that the copper is a 2+ charge, because those can change. Copper can form a 2 or a 1, I believe, whereas like iron can form a 3 or a 2. But you don't have to know that. It's going to tell you that in the name. Now, when you go from formula to name, which is this question, that's where you have to identify what the charge is based on the formula. Those are probably the hardest ones, where it's a transition metal, so you know you need to use Roman numerals, but you have to deduce that from the formula. So we'll do those in a second. So copper 2 chloride, just to finish this one off, that's going to be the 2 charges. So the formula is going to be CuCl2. So A and D are really similar in that you have that same 1:2 ratio. It's just that in D, you're not told what the charge is on the calcium because you get it from the periodic table. In A, it's a transition metal, so they have to tell you what the charge is. Okay. I said A and B, so we'll go ahead and do that. So sodium +1 because it's in the first column. Sulfur 2- because it's in the 6th column. So the formula there is Na2S. So now a 2-to-1 ratio. And this would be called sodium sulfide. In almost all of the naming, we change the last one to "ide." The only time we don't do that is the polyatomic ions. So, like if it was SO3 instead of just S, we call that sulfide to indicate we're talking about the sulfur element, whereas this one, we call it sulfate. Sulfate would be this guy. Okay, so we don't change that. We don't change those endings at all so that we can tell the difference between those. Okay, and like I said, this is the last one's a little bit trickier. For A and B, these are both transition metals. So we need to be able to identify the charge. So if we know that chlorine is a -1, then that means that if there had to be 4 of them, tin must have been a 4 charge. So it would be tin 4 chloride. Because if I had Cl- and I needed 4 of them to balance those out, I must have needed just 1 tin 4. Lead PbI2 is going to be lead 2 iodide. And then maybe just as a reminder for C, when you get these more complicated ones, or really you could do it for the simpler ones too, the easiest way to identify this is take the number that's opposite. That's going to be the charge up here, which is what we would expect it to be. Oxygen should be -2. And then that 3 can come up to the iron and tell us that that's iron 3. So you could like draw them out and say, oh, there's 3 O2 minus So how many ions, if there's 2 ions, what does the charge have to be on each of those? And then you'll figure out that it's 3 plus. So you can do it that way, or you can do this like reversing the charge, reversing the subscript to give you the charge. So iron 3 oxide. Okay, questions on those, because those tend to be a little bit confusing. If you go back to your notes from when we did this in chapter 3, you'll see like we did a flow chart. There's one from the book, but we also did one. It's like, figure out, is it a covalent or ionic? If it's ionic, is it transition metal or not? Okay, 48 and 50, let's do those together. A and B, both. These are our covalent ones now. There's lots of naming practice in the chapter 3 folder on Blackboard if you need it. I didn't set a timer apparently. I was like, why isn't that ringing yet? Okay, so first 2 here, these are both sulfur oxygen compounds. Good reminder that the ratio can be different for covalent. This is where we use prefixes. We still change the ending to "ide." The only one to remember, or the only thing to remember, is that with the prefixes, we don't say mono if it's the first one. Okay, so both of these would just be sulfur, and then this one would be trioxide, and the next one would be dioxide. Okay, for something like D, this would be nitrogen, not mono, because it's the first one, but the second one would be mono. Then when we do formulas, it's probably even easier because it's just telling you how many there are. So boron, tribromide, 3 borons. Sorry, 3 bromines for every 1 boron. Dichlorine, so 2 chlorines, 1 oxygen, etc. Okay, so moving on to the calculations. I'm going to do not a ton of these just because I want to make sure to leave time to do like limiting reactant problems, which I know throws people off a lot of the time. So we're going to skip over the calculating the formula mass because this is something you do as part of mole calculations. It just means look up magnesium, look up bromine times 2. That's the formula mass. So let's use that to do 62A on both and 64A. So going from moles to grams and then going from grams to moles. These should feel pretty straightforward. Again, you'll use them a ton as you do the stoichiometry problems. Also, vitamin D3 has been shown to improve seasonal depression. So I'm going to Amazon some of those right away. They have gummies. All good. Okay, so I'll start doing those up here. And I know you guys really care, but free overnight shipping. It's all good. I'm very excited. Because I'm sure it's going to make all the difference, right? Ooh, that's not right. CF2, CL2, okay. So, like I said, molar masses, we had to do that to get this one. We had to do that to get this one. So, that's incorporated into these calculations. So first one, we're multiplying because we need the grams over the moles, so the moles cancel. Second one, we just flip that. And then the last thing in chapter 3 that I want to look at is the percent composition, or mass percent. So we're just going to do the first one. And what it's saying is how much does each element contribute if you have, contribute by mass, if you have, you know, whatever, 100 grams or 1,000 grams or 5 grams, what percentage of that is nitrogen, what percentage of that is oxygen. So if we want it for nitrogen, we're just going to take the mass of nitrogen, but we have 2 moles or 2 atoms for every 1 molecule or mole of molecules. So we need to do the mass of nitrogen times 2 and then over the total molar mass, which now just includes oxygen. Okay, so I think this comes out to be 64%. So times 100, because we need to do per cent, century, 100, so per 100. Just double checking I remembered that right. Yeah, 64%. So what we're saying there is that then 36% would be coming from oxygen by mass. Obviously by moles, that's not the case. It's a 2-to-1 ratio. Or you could think of that as like 60, oh, it's kind of close, 67% nitrogen by moles or by atoms, but by mass, it's only 64%. It becomes more dramatic when you have something like hydrogen that's really, really small, because it contributes a lot by atoms, but not a lot by mass. Okay, moving on to 4. So very limited number of topics here. Balanced chemical equations, and then stoichiometry. Part of stoichiometry is the more involved problems that are limiting reactant problems, but it's still stoichiometry. We will continue doing stoichiometry, though, in 5 and 6. So don't think of it as like its own little topic. It's just you're practicing it grams to grams in chapter 4. Then you're going to do it molarity to moles in chapter 5. Then you're going to do it ideal gas to moles in chapter 6. So you'll do lots of limiting reactant problems when you're studying 3 and 4 as well as 5 and 6. So let's start with this one, which you have to actually write out the equation and then balance it. We'll just do 1 for balancing equations. Okay, so this is an interesting one because it is, when we did chapter 4, we introduced the idea of a combustion reaction, which is burning. So that was like a carbon hydrogen compound, sometimes with oxygen in it, reacting with oxygen gas to form CO2 and water. This is the reverse of that, which I love because this is showing you what plants do, which is literally the reverse of burning gasoline. Okay? The carbon hydrogen compound we use when we're burning gasoline is obviously different than the sugar that plants produce, but otherwise it is the same thing. Instead, or the reverse thing. So we're taking the CO2 and water and turning it back into plant material, sugars, and then it gives off oxygen, which is what we, know trees do, plants do, they give off oxygen. Okay? When we're balancing it, the biggest thing to remember here is that this sugar compound has some of the oxygen in it, so don't forget that when you're counting up the oxygens. So we put a 6 in front of the carbon here to give us the 6 carbons, a 6 in front of the water to give us the 12 hydrogens, and then we just have to look at the oxygens to figure out how much O2. So 12 from here, 6 from here, so 18. And then we have 6 coming from the glucose, so we actually only need 12 coming from the O2. So the the coefficient there is also 6. And there's another balancing one further on that you guys, 4 balancing ones that you guys can do on your own. There's also a worksheet, I think, posted under the chapter 4 folder. Let's go ahead and do 32 for our first stoichiometry problem. So this is 2 different parts. If you just get to the first one, that's fine. Starting with 15.2 grams of aluminum, how much H2SO4 do you need in order to react with that? And then if you have time for the second one, they also ask how much H2 is produced. Okay, so not limiting reactants here, just starting with the aluminum itself. Okay, so this is good because I don't think we've done, although we did a ton of these and it will make up a significant portion of the final exam, we haven't done them for like a month, right? Because 8 and 9 were lots of concept stuff. So good reminder, and again, we'll keep doing them in 5 and 6. So what I always recommend is don't fill in these numbers until you set up the units. Then go back and figure out what the numbers are. So aluminum from the periodic table, these guys from the coefficients in the balanced equation, and then this from the periodic table, but add it together. Okay? And then when you're doing the H2 one, you would do the exact same thing at the beginning, but then here you'd go 2 moles of aluminum to 3 moles of H2 rather than H2SO4. Then you would do the mass for the hydrogen instead of H2SO4. Okay? So very similar approach, but just changing that now you're going to product rather than comparing 2 reactants. So for our last one, we're going to do a limiting reactant problem. We'll do 44. And don't get confused by this. It says calculate the theoretical yield. That's just the calculated value. Actual yield is if you do an experiment in the lab, in a laboratory setting, you get a certain amount. It's not always, it's never, I'll say, 'cause it just doesn't happen that you get 100% yield. You're never going to get the amount that you expect to from the calculation. So that would be called the actual yield. And I don't think I gave a sample problem of this, but I'll just write it down here. Percent yield would be you take the actual over the theoretical, which again is just the calculated value times 100. Okay, so here they're just saying do the calculation and tell us how much you think you could get from these two. So go ahead and work this one. Give you like 4 minutes and then we'll have time to go over it. Okay, so on this one, I've done the units, and now I'm going back to put in the masses. Or sorry, the numbers. I didn't think that was right. I was like, that seems way too high. I just Googled it instead of, because I thought I couldn't read it up there. Okay, sorry about that. I got the mass wrong there. It's 47.867. I need to change that in this one too. Okay, so key point, don't miss this part. You got to compare the two and see which one's the smallest. So this one comes out to be 12.9 grams, whereas the second one comes out to be 8.1 grams or 1.5, okay? So this is how much you actually will make, and F2 is the limiting reactant. Okay, you cannot make more because you ran out of F2. Okay, 5 and 6 on Friday. Hi. Yes. Will you take it? Okay, I'm going to do that. Friday? In class? Or it's going to be tough because I anticipate it's going to be crummy with her. I'm worried they're going to have to delay it. So we can try for Friday. If not, we can do Monday. Okay? All right.